Okay, I'm going to start this video as I usually do on these Heathkit test equipment documentaries. And start with Chuck Penson's excellent book, Heathkit Test Equipment Products. Flipping to the appropriate section, I'm going to be talking about the IM-102. This was Heathkit's first digital multimeter, coming out in 1972. It was not an original design of theirs, at least the circuit wasn't. The case and the circuit board and all the practical details were their design. But, and part of a series that included quite a few different frequency counters, all like this and such. But it was actually a Weston product. At that time, Weston and Heathkit were part of the same company, or, you know, under the same parent company or something like that. I'm not sure the exact relationship, but they were somehow joined at the hip. And there were a number of VOMs that Heathkit put out that were spitting images of Weston versions. This one here, even though the circuit is virtually identical to a Weston 1240 or 1240 digital multimeter, you know, all the practical details are Heathkit's. I think they even use their own models of Nixie tubes, but with, I think, one exception, all of the ICs are the same kinds of ICs. Heathkit did use their own choices of transistors and diodes, but they're equivalent to the ones Weston had. And I believe that the main range switch is the same essential switch as the one Weston used, although the various wafers, which can slide along the length of the shaft, are positioned differently or spaced differently to accommodate Heathkit's somewhat different circuit board layout. Anyway, so Heathkit's first DMM, but not a completely original Heathkit design. Came out in 72, as I already said, and they continued it through 1978. It was considered quite expensive, $250 in kit form back in 1972. That's a lot of dough. It's not at all an inexpensive meter. On the other hand, it has quite good specifications. After all, the Weston wasn't a hobbyist product, so they were designing their meters to a higher standard, and so Heathkit's sort of gets dragged along into a somewhat higher realm than they usually targeted their products towards. At the same time, the same year, Heathkit maybe realized that while they're copying a Weston meter, it's too expensive for many of their customers, and they need to have something more competitive and hobbyist-oriented. So they came out with the IM-1202, also in 1972, and there that is. I already have a video on that. It's actually a video that combines the IM-1202, the IM-1210, and the IM-1212. These all followed in sequence. So this one came out, it was only out for 3 years, and then Heathkit rearranged the components into a case that they thought was more modern looking. This one was in a package that was obviously set to mimic Heathkit's existing series of vacuum tube voltmeters, or VTVMs. So they repackaged the electronics, cheapened it just a little bit. This was still probably a little higher than they perhaps thought it should cost, although the 1212 cost exactly the same amount. The main difference here is that they left off the range, or the polarity swap switch. So if you had the test leads connected backwards, you could throw the switch and change it. Here you would just have to move the test leads. Otherwise, it's the same animal in a different case. And then, as I already mentioned in my previous video, the IM-1210 is essentially the same circuit as this, except for the display section is modified to use the more modern LEDs And they also went through and did some penny pinching in the circuit, deleting a number of components that they thought probably weren't absolutely necessary, things that might slightly reduce stability or accuracy and so on slightly, but with only a 2.5 digit design as all these had, the resolution is so low that, you know, why bother with having great accuracy? Still useful meters, just at the very low end. About halfway through the period of time when Heath offered the IM-102, they introduced a mid-range digital multimeter, the very nice looking IM-2202. This was their only portable digital multimeter at that time. It was their third model, just because these two hadn't come out yet. It was set up to have an internal battery as an option, so it could be carried around and used without being plugged into the AC power. It had a beautiful Panoplex display. Right around that time, Heath seemed to be kind of hooked on the idea of using Panoplex displays in their new products that needed digital readouts. Some of their later model power supplies use Panoplex displays also. I have a video on this meter. It's a pretty nice meter. The only thing I don't like is having to futz around with these 4 buttons along with changing the range. It seems like you're constantly pushing buttons and turning knobs to use it, which can make it a little frustrating, especially if you're used to modern multi-ranging digital multimeters. Although at the time it was probably considered the bee's knees. Then Heathkit came out with, in 1979, about halfway through the period of this one, and 1 year after the IM-102 was discontinued the end of '78, it was a last call in the Christmas 1978 catalog. And this is probably considered its replacement. It's a higher end meter, a lot of steps taken to improve stability and accuracy. And it is also Heathkit's only auto-ranging meter. Notice that the selector switch only picks function, not range. So, very nice meter. I also have a video on this one. But then again, this was getting into the same price range as the original IM-102. You know, close to $300. Well, this was $248 or $249, basically 250 bucks. And this was closer to $300, so possibly Heathkit's most expensive digital multimeter. Well, I'm certain it is, actually. Because this was now getting to be their more serious offering in digital multimeters, Heathkit did follow up by coming out with a series of 3 similar looking digital multimeters. They all came out in 1982. The IM-2260 had an LED display and was fairly basic but pretty nice specifications. The IM-2262 had an LCD display but was otherwise nearly identical. They did add a range to it, I think on the low end. I have videos on both of these meters if you want to see them in more detail. And then the 2264 was essentially the same as the 2262 with the LCD display, but they also added a trending meter or a peak reading meter, which could be useful in several different ways. And I believe they also added a alarm, so you could set it up to alarm if you know, the thing being measured, for example, voltage, got into a certain range or out of a certain range. And it also has a beeper in it, so if you're doing continuity tests you can hear it. There's also a alarm LED that flashes. Heathkit didn't keep the 2262 in the catalog for long, although it's clear that all 3 of these meters were developed at the same time and you know, not developed one after the other. They were clearly all designed and production started at the same time. They probably discontinued the 2262 because it was too similar to the 2264. Yes, it costs an extra $50, still kind of a pricey meter. And at a time when competing meters were getting to be a lot less expensive. Still, for a non-auto ranging meter, this is a pretty nice meter, as are the other ones, really. The 2264 ended in 1987, and the 2260, the cheapest of the three, and the one I still prefer the LED display to the LCDs. The early LCDs were not that good, kind of small, hard to see from various angles, and not backlit, so you needed good room lighting from the right angle to see them clearly. Whereas the LED one was obviously a lot easier to use in many situations, and they carried that up to 1991, which is when they exited the kit business. So it went up to the bitter end. And while I'm just talking about digital multimeter history at Heathkit, they did also have, coming out in 1979, fairly early, their answer to the early Fluke handheld digital multimeters, their IM-2215, which they kept around for quite a while, and then replaced it in 1987 with the IM-2320, which they also kept almost up to the bitter end, up to 1990. I have videos on all of these in considerable detail if you should care to peruse them. Now back to the IM-102. In my video where I talked about the less expensive Heathkit DMMs, I briefly showed my IM-102. It had had a lot of damage, and I considered it unrepairable. And I obtained another one which was also just too badly trashed, and then I obtained a third one which was at least salvageable. I still had to do a number of things to it, but that one is the one that will be presented in this video, meter number 3 of my 3 IM-102s. The other one sadly went to electronics recycling after I stripped off some knobs and things that I was able to resell on eBay. So I just got the case top and bottom sitting in a bath of warm soapy water for a while prior to getting them repainted. I got some different paint from what I usually use on these Heathkit cases because of the color. It's a darker color they used for a while, and I can't approximate it with any of the spray paints available to me. So I tried a bigger store, the local Benjamin Moore, which is also called J.C. Licht. I don't know if it's a parent company or how that works out. Ultra Spec Maintenance Coatings. It's an acrylic low luster enamel. We did some samples out of here prior to coloring it, and it looked like it had about the right finish once dried. And we're going with the Benjamin Moore Color Chip 1000, which is just about exactly the same color as the original case, and I've had a quart of it mixed up here. Color 1000, Northwood Brown, and this obviously can't be sprayed on easily, so I've got a roller, and I'm hoping that does an okay job. After all, it is a textured surface already. And I've just painted the two case halves, the shells, using this paint that I described just a moment ago. Put it on with a roller. That's necessarily giving it a somewhat different texture than the slightly pebbled finish that was on the paint underneath it, but I think it'll be alright. It's sort of a cross between that and a crinkle finish, which certainly a lot of Heathkits from this period had. So I think unless it gets really weird when it dries, it should be okay. The color looks about right. Okay, next morning, these came out pretty good. The texture seems okay. It's not quite the original, but it's a good texture. One of the two knobs has a crack in it, a small one, and I filled it with epoxy and letting it dry. So that shouldn't get any bigger, hopefully. Well, I discovered that the internal slide nut for the front panel neon bulb housing is missing, so I've kind of extrapolated what I think the original dimensions would be. I've got a piece of 1/8 inch thick aluminum from my scrap pile. Got it marked out here to cut out, and then I'll have to drill and tap a 632 hole in the middle, and hopefully that will do the trick. Alright, there's the new nut with a length trimmed 632 screw going into it. That should do the trick. Alright, that was real fiddly to get that in there, but there's the screw head. And there's the aluminum nut inside the molded plastic neon lamp holder. By loosening the screw, I can slide the holder a little bit frontwards or backwards. But this is a big improvement over the way it was just flopping around in the breeze before. The other thing I made for this was this banner was missing. It just is a strip of something, probably some sort of plastic that was glued in there into the metal bezel. I looked at a lot of photos of the originals and from other models in the series, and pretty much divined the character size, position on the front panel, and the fonts. I had to approximate with the Heathkit logo. I couldn't find anything. I probably found about 20 fonts that were nearly identical, but they were all off in some small way. The actual Heathkit font that they used was almost uniform thickness. So whereas this one it's got all the right shapes, and the serifs and everything are about the same, but you can see the tapering on the serifs on the ends of the T. They would have just been straight lines on the original Heathkit. Anyway, this was the closest font I had on my computer. And this is essentially just Arial. It's a real close match. And I set this up in my page layout software and fuddled around with it, made a few test prints, got the positioning just right, printed it out on some Kodak print-to-last paper. Is it Kodak that made that? No, 3M. 3M print-to-last paper. Printed on the laser printer and then stuck it on there, and then I managed to scratch it. Stupidly, I thought I was grabbing for this tool here, which I don't think would have scratched it, and initially I grabbed a screwdriver instead, and before I knew it I'd managed to put a couple little dings in the toner. But I thought, well, that's in line with the rest of the wear and tear on here. I stuck it down there with some permanent adhesive, and it'll do the trick. It's a real close approximation of the original. The only capacitors I've changed are these two electrolytics here. A 250 microfarad 50 volt DC rated electrolytic, and a 2200 microfarad 25 volt electrolytic. I believe the original was 2000 microfarads, and I went up to 2200 because that's standard size now. I think the voltage ratings are the same, 250 at 50 and 25 volts. Those are just modern Cornell Dublier or whatever they call themselves, or Illinois capacitor. I think they might all be the same company now. Anyway, hopefully I haven't screwed anything else up that was working before. I put a post-it note, just the top of the post-it note there, identifying the pinouts and other information about the two dual transistor packages. And in the course of my scoping this thing out, I discovered that these two fuse holders were reversed, top and bottom, from what the Heathkit manual said. Whoever built it either decided to do it different or just screwed up. But I traced the wiring and it certainly goes to the right place. So I've labeled them with some brother labels, P-touch type, and F101 for the volts ohms input fuse. It's a 1/4 amp fast blow. F102 is the milliamp input fuse, 3 amp fast blow. And F301 is the AC line fuse, 1/4 amp slow blow. So that's sorted out. I don't really think there's anything else that I need to do on this. Okay, here's the artifact. As I'll discuss elsewhere in the video, I had to make a new nameplate banner for it. There's a blotch on the paint that I could not correct. There's some corroded areas on the bezel that I painted over. A previous owner had re-glued this plastic window on, and it's still a little loose, but at least it's held down at the corners, so I'm not going to mess with it. A volts and ohms jack, the common jack, and the jack that's used only for measuring milliamps. This is the general function switch, but the function is also controlled by the range switch. So you have an off position, that's the power off, and then 4 positions for volts and milliamps, sort of, but then there's also a 200 millivolts and 200 microamps position. And then there are 6 resistance ranges / functions. And within that you have to select whether you're measuring DC milliamps or DC volts or ohms, or AC milliamps or AC volts. Ohms would always be on the DC side. You can clearly see the 3 Nixie tubes here, and also the 1 neon bulb that acts as the 1 for the leftmost position. So it's capable of reading up to 1999. Again, typical of Heathkit, one of their cost-cutting steps with these meters was to not put an extra Nixie tube in for the position that's only going to show a 1. The higher end stuff probably did use a Nixie tube for that, but I don't think they were alone in this tactic. I always thought it looks a little cheesy, but that's what they've done. There are also, you can see kind of here, a plus and a minus. That would be a polarity indication and also an overrange indication. Each of those is lit up by a separate neon bulb behind the window here. And of course, again, you've got this 1 neon bulb here which just lights up to show a 1. Here's the overview. Power transformer in the back. The main filter capacitors for the power supply, plus and minus 12 volts, are here. The primary calibration potentiometers are here with holes in the back to access them without opening the cabinet. These are a couple of custom or proprietary dual transistor packages, so they've got two transistors probably touching each other, you know, face to face, back to back, whatever, and then potted or encapsulated into this little housing, and those plug into little receptacles on the circuit board. Those are used for the integrator function. This capacitor here is probably the main integration capacitor for the analog to digital converter. I see one here, I'm not sure, it's either this one or this one that's the primary integrator. These are op amps here in these round cans. That was a more common package for op amps at the time this was designed. There's a trim pod here, which is for the 2-volt full scale adjustment, something that is only likely to need being done once. And there's a 200 meg adjustment here, also not accessible from the outside. This is a custom high precision resistor network. So it takes the place of a bunch of discrete precision resistors, and they're probably wire wounds in there. This is the back side of the main switch. And this is the back side of this switch as far as where they terminate to the circuit boards. We have some resistors here which are probably for the ohm or the current shunts based on their wattages. These here are all Fairchild RTL logic chips. These would be counters and display drivers and so on. They're all associated with the counting function and display or Nixie tube driving function. These other chips here are logic chips. I haven't checked yet to see what family they are, but they might be RTL as well. These are just simple gate packages, ands and ors and so on. This is a test point adjust pot, again something that shouldn't need to be messed with too often. And I don't remember what this guy is doing back here.
The 7271.
This is one of the voltage regulator parts, but I think this is probably going to turn out to be a series pass transistor instead of a 3-terminal voltage regulator. Okay, here's the back side of the circuit board. We have actual view of the switches here, the two function / range switches. Most of the switch pins go directly into the circuit board. Those are these white wafers here and here. This gray one here has side terminals for just hooking up wires, and that's some of these components right around here. This one here is set up to have PC board pins, so the pins go into the circuit board. All of these go into the main circuit board, and these two gray wafers here are for some of the discrete wiring going around here. Over here we have the 3 fuses, none of them accessible without opening the case. This is the fuse for the power transformer. This is the 3 amp fuse that's in series with the milliamp jack on the front panel, so that would blow if you have too much current. And this one's a 1/4 amp fuse, which is involved in the ohms measurement circuit. The back of the 3 jacks, everything is wired out from here. It doesn't go directly to the circuit board, but they either go to the circuit board over here or to one of the fuses or some other place like a switch. Now this daughter board here is the precision AC to DC converter. There's another op-amp in a can here, and the AC calibration potentiometer. And there are some components on here, capacitors, trim capacitors, which are involved with fine-tuning the response of the converter at different frequencies and so on. This doesn't use a plug connector to plug into the board. It actually just has wire jumpers soldered on at various points. And there's some more over here, which are then just bent and go straight down the pads on the main circuit board. The rear panel, this area is a little boogered up because there was a big label that was physically glued onto here from some previous owner, I think. And in the process of getting that off, a few of the letters came off here. This is the oddball type of AC line cord connector that Heathkit was using on some equipment at this time. I think they soon abandoned it, but it was a thing for a while, and I have a couple of other meters that came out not long after this which use the same type of plug. At least this one came with, I think, the original power cord, so I didn't have to go hunting around for a compatible power cord. And you can see the 4 holes for the adjustment pots. The Heathkit label could be positioned in 2 different places. Up high like this, where it would leave the wired for 120 volt AC exposed, or you could put the label down further and leave, I presume there's a wired for 240 volt AC message under the label. And then there's a little chart here for do not exceed values for AC and DC in different positions. Alright, let's turn this guy on. Sitting pretty close to 0. And I'm going to put this in the 2 volt range and set up for DC volts. We have 0.014 volt just quiescent floating around here. That was with the leads open. Now I've engaged my power supply, so the power supply is now connected to the leads. And I'm going to take it up to 1 volt. Notice that it switched to the plus illumination, and it's showing a nice clear 1.000. When it's flashing over like that, I've exceeded the range. Even though it's on the 2 volt range, that really means 1.999. I'm giving it 2 volts, so it's overranged. So I'll switch up to the 20 volt range, and I get a nice clean 1.99 or 2, depending on what it wants to do at the moment. Go back to 1 volt, go back to here. Okay, let's go up to 3 volts, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. We're about ready to overrange it. That's 20, and I'm getting the overrange flashing there. So I'll switch up to 200 volts. And it's reading about 20 volts, pretty good. 21, 22, 23, 24, and that's a size, 25, 26, 27, 28, 29, 30, 31, 32, and that's as high as this bench power supply goes. So I'll take it back to like 24 volts. So DC volts is working fine. Okay, I've switched it over to the 20 milliamp range and the DC milliamp function. I have my 4 to 20 milliamp loop tester here, and the power supply is set for 24 volts, which is pretty common. And when I turn it on, it goes to 4 milliamps, which is the minimum. As I roll this up, it's going to increase. And when it says 12, the knob should be in the middle, which it is. When I go up to 20, of course, it overranges, so I have to back it off just a little bit. Just under 20 here. So DC milliamps is working fine. Okay, I've got the range switch set to 200 volts and the function switch set to AC volts. I have the volts and comms test lead jacks used. Those are connected to my AC access panel, which is plugged into my Variac, and I'm going to turn that on and crank it up to about 50 volts approximately. And then I have to turn this switch on. Just about 50 volts. I can even bring it in here a little bit closer. And let's raise it up. Well, it says 100. And the Variac is saying 100. Take it up till it says 120. And we're right on the 120 there. So the AC volts is working just fine. Alright, I have it set to the DC volts and ohms position, and this one's set to the 200 ohm range. And it's just running around there because there's no connection to it right now. The test leads are hooked up to this Heathkit decade resistance box, but everything's set to the 0 position, and this model I don't believe shorts the leads out. Let's see if I actually short the leads out. Yeah, then we get a nice stable number closer to 0. So let's take it up to it wants to have a quiescent resistance of about 2 ohms. So right now I'm setting it to 10 ohms right here, or yeah, 10 ohms, and it's giving me 11.2. 50 volt or 50 ohms is taking me up to 53. And I'm overranged at 200 ohms. I'll take it back to 100 ohms. And it's pretty good. I'll have to go up to the 2K position where it's in 2K now, so it's only reading 100 ohms, so 2K would be essentially 1.999, so 0.1 for 100 ohms is appropriate, and it's still showing the quiescent 2 ohms that's just in the test leads and stuff. Let's go up to 700 ohms, 0.7K. Let's go to 2K, and it's overranged, so I'll go up to 20K, and it's giving me a nice 2K. Let's go to 8K. That's looking pretty good. Let's go to 10K on the 10K switch. That's looking good. When I go to 20, it's going to overrange. So I'll go up to 200K. And it's showing me the 20 point small inaccuracy there. 40, 71, so it's pretty close. And let's go to 300K, and it's overrange, so I'll go up to the 2 meg range, and 0.3 megs is 300K, so the ohms functioning is working quite well. Okay, there's the beauty shot. Alright, let's take a look at the Heathkit manual. This is a printed out one that I made from a download, and it's a partial download. It does not have the assembly portion of the original manual. Because it's a fairly complicated product, the manual is fairly thick. We start out with the first page, table of contents, picture of the product. We go into the introduction. The Heathkit model IM-102 digital multimeter is an instrument that performs accurate voltage, current, and resistance measurements, which it displays on cold cathode display tubes and other lamps. Except for these display devices, solid-state circuitry is used throughout the instrument. The multimeter is housed in a low-profile metal cabinet with a convenient carrying handle. This handle can also be used to support the front of the instrument at a more convenient viewing angle. The convenience, versatility, and accuracy of this modern unit make it a very desirable instrument for the laboratory, the service shop, or the ham shack. And then we go into the parts lists. Quite a few pages of that. And I put in a pink sheet here just to differentiate that from where the manual jumps ahead to. This would be all of the assembly instructions in here, of which I'm sure there's a great many pages. I'm into the end of the assembly where it's talking about finishing up making the test leads and doing the initial tests, the calibration, which interestingly enough here seems to be done mostly by a chart instead of a bunch of step-by-step instructions. And that does have steps, it's just that it's presented in chart form instead of paragraphs with checkboxes. And that's continued on another page. AC frequency compensation, final assembly. One thing I'm missing on mine, you're supposed to have a cardboard light shield surrounding the Nixie tubes. Although when the case is closed, you don't really need that as far as I can tell. So, and typical Heathkit, when it comes to things like this, they often did a nice job elsewhere, and then they would kludge something like this together. You know, glue a little piece of cardboard to the circuit board, and this is apparently an adhesive, one-side adhesive cardboard that you have to cut out according to a pattern. They give you all the information there. I guess it already has some holes pre-punched. You fold it up. Because one side is sticky, it sticks together. Remove protective backing. And you end up with this thing that's sticky on the outside, or I guess actually on the inside surface. And then you put the fourth hole over the top of the neon bulb, which is clipped into the lamp housing, which in turn is mounted to the circuit board. And with all the tops of the tubes sticking through the holes, everything is kept in alignment. and it also provides a backlight shield for the Nixies. I do not have that on mine, and I thought briefly about making a 3D printed one, decided it was going to be a waste of time. Not something required. I do think there might be a slight advantage, actually. If you're in a room with quite a lot of ambient light on it, enough light can go in through the front window, past the tubes, slightly illuminate some things on the circuit board, and then that can be vaguely seen through the window. Having something like this would certainly alleviate that if it were a problem. Final assembly, putting the case together. Then we go into the operation. Lots of diagrams. Kind of interesting how they made a squashed version of the panel. Various high voltage areas on the circuit board, a warning about that. More instructions. I guess it's nice that they have a separate picture for each type of measurement, so you don't have to keep flipping back to the picture. Then the in case of difficulty section, visual test, checking waveforms, the troubleshooting chart. Not an extremely large one. Voltage chart diagram for the smaller AC converter circuit board, and a similar thing for the large main board. Oscilloscope waveform patterns, telling you where to probe on the various ICs to get the different traces, or on a diode. And then there's a block diagram of basically the logic that operates the counting part of the meter. Specifications. A somewhat misplaced timing diagram, which goes with that block diagram, and the schematic. And then we're back into the specifications again. I made some sort of an error there with putting that page in a less than ideal spot. Then we get into the circuit description. I don't know about the assembly part of this manual, but this manual is crawling with errors. I've seen mistakes in Heathkit manuals before, but this one, I don't know if it's an early edition of it or what, but it's just chock full of flat-out mistakes or just unwieldy language, you know, written by an unskilled technical writer, or maybe by an engineer with no technical writing skill. Anyway, yeah, I did read through it, kind of curious to see how they described it, and a lot of it is just, you know, they'll call out the wrong components and you get confused. They'll say positive when they mean negative, and just all sorts of stuff. Anyway, quite a bit of description though. And they've got these nice broken out diagrams to focus in on the parts that they're talking about. And those aren't free of errors either. I've got little pencil notes on here, you know, talking about things I discovered that they had wrong. Still going on. Lots of description. Then a very confusing section on the DC calibrator, which is apparently something that came with the meter, which I don't have. Another circuit board, essentially, just a tiny little one. But it's one of those things you wouldn't need these days if you're just restoring one. It would only be necessary if you had no other test equipment and you're trying to build one of these and calibrate it. X-ray views of the AC converter board shown from either side. Unfortunately, these are double-sided boards, and they would normally be, I think, red and blue or something like that, two different colors. And I think the blue doesn't reproduce on the xerographic copies, so you really only get one side of the circuits. I was trying to trace a lot of things out, and without being able to see all the circuits clearly, you know, all the foils and things under the components, it's hard to trace things out. So again, front and rear views or top and bottom views of the main circuit board. Some poorly reproduced chassis photographs. IC identification chart. Quite a few pages talking about the various ICs, their pinouts, and so on. Transistors and display tubes chart. I was having a heck of a time because almost all of the transistors Heathkit mentioned in here are types that are pretty hard to find out what they are. And Heathkit doesn't tell you what they are, they just give you a manufacturer's type but don't give you a further explanation, and then you can't find data sheets on the manufacturer's numbers. So I actually resorted to a manual I bought on eBay for the Weston 1240 and kind of worked backwards from the components they used, and that helped me locate some specs on some of these parts. Took me a lot of time to get as far as I did, especially these dual transistor packages, trying to figure out what they were and compensating for the errors in Heathkit's documentation. I finally figured out what they were. Sprague parts, and the TD101, TD401, there are Sprague part numbers. Diodes, once again, just somewhat of a nightmare trying to identify what these are, what their specs are. Got a lot of penciled notes in here. There's a number of web pages that show a lot of replacement parts and parts identification by Heathkit part number. And in a lot of these parts I found some glaring errors on those websites. Unfortunately, almost none of them seem to be maintained, and most of them just copy each other, so they all have the same mistakes. I copied out some pages on the Sprague dual transistor packages, which aren't bound in. A switch pin locator, which seems to have some issues, doesn't match the circuit board. And then I reproduced the big fold-out schematic diagram, which came in pieces in the download that I had, so I had to print them out and stick them together with tape. Also a page of schematic notes. And then I put another divider in here, and for all the ICs that I was able to eventually find data sheets on, I printed all those out and stuck them in the back of the manual that I have. As soon as I finished that, then I found one of them popped up on eBay, the original manual, so I've got that on order. Okay, enough about the manual. Before I get into the circuit description of the IM-102, I do want to mention briefly my manual for the Weston 1240, which seems like a crappy Xerox of a manual, but I mean, I think that maybe this is what actually came from Weston. You know, I don't know. It's possible somebody xerographically reproduced the original manual and bound it and cut it to size and everything, but I'm guessing this is an original manual, just poor reproduction on Weston's part. So it looks like this, and I'll show a photo of it, a clearer photo, elsewhere in this video. Even though this is small, it has pretty much all the stuff that is in the Heathkit manual, just in a smaller format. And if you want evidence of the heredity of the IM-102 from the 1240, this manual reveals a lot of it. And by the way, Chuck Penson's book on Heathkit test equipment products did not mention the relationship between the two meters, so I've let him know about that. So everything's just a little more compact. So the only practical difference besides just case layout and graphics and things is that the Weston 1240 used a set of 4 radio buttons. Only one of them can be pushed. When you push one, the other 3 pop out. And 2 of them are for DC, 2 of them are for AC, and then you can pick volts and ohms or milliamps. And on AC, milliamps or volts. There's no ohms in AC. But the rotary range switch is identical between the 2 meters. The style of knob is different, but all the positions are the same. And indeed, all the contacts on these switches have exact copies in the Heathkit version, which is operated as a rotary switch, but the exact number of contacts and how they open and close in different combinations is exactly the same between the 2. No difference in the circuit. Anyway, there are calibration instructions in here, and it actually has the same exact timing diagram as the Heathkit one. And their circuit description, parts of it are word for word the same. Obviously Heathkit copied, but other places Heathkit went off on their own or just changed a few words and so on. And when they went further afield from the Weston one, they started making a lot of mistakes. You know, whoever did the rewording, rethinking of certain paragraphs often put their foot in it. I studied the circuit in considerable detail on this meter on my own, and only when I found a few sticking points did I go back and read the Heathkit and the Weston ones and compared notes. And there were a couple places where I just couldn't understand how something was supposed to be working. I knew what it was supposed to do, but how it was accomplishing it with the circuit I was seeing in the schematic was confusing me. And the Heathkit description either didn't help or made things worse. And the clarity of the writing in those sections in the Weston one was superior, and actually gave my brain the kickstart it needed to get past the areas I was hung up on. But they have these tiny little diagrams with, you know, they're obviously hand drawn and then reduced, and just often very hard to read. But they do have the similar breakout schematic sections in here like Heathkit did. They don't have as many of them, but they do have a lot of them. And indeed, for example, this diagram here is exactly reproduced. Well, I mean, the exact layout is reproduced, but drawn in the Heathkit style, so small differences. Anyway, this is the 1240, and this video is not about the 1240. I should mention in the heredity department, the plastic holder for the 4 neon bulbs that augment the Nixie tubes seems to be exactly the same, so I think Heathkit either closely copied Weston's lamp holder or they just bought them from Weston. And the circuit board layout, at least up in the front end, is very similar. As you would figure, sometimes form just follows function, but I bet they had the circuit or the circuit board layout in front of them when they designed their version over at Heathkit. The schematic here is tiny. This is ridiculously small. Very hard to make out the words. Luckily, this is a fairly clear copy, and with a jeweler's loop I was able to actually read most of the text. It was still clear enough in the reproduction that it was possible to read it. I think Heathkit's diagram when it came to the logic is considerably better than Weston's, and they certainly rearranged this substantially. And of course then there's more parts lists and so on, but that's just a peek at the Weston manual. Well, this is the Heathkit schematic with all my markups on it. The only other copy I have handy is the one that's folded up in the book, and that'll be too hard to shoot video of. But I'm not going to rely on this anyway because it's too hard to read and the layout is confusing. So just to give you a quick look at the layout of the schematic, Heathkit did this goofy thing here which really confused me at first. It was hard to trace wires through. I kept getting lost and jumping to other wires. I don't know what they thought they were doing there. I don't think it made things better. Let's see, they had some mistakes on the drawing there. I've got also some annotations on here regarding where things are different from the Weston circuit, only in a few places and very minor differences. One thing that Weston did do, just in case anybody's wondering what the differences are, is Weston seemed to like doing factory calibrations that relied on selected components. I've seen that on other Weston meters that I have, VOMs, where Heathkit might put a trim pod in for something and Weston instead would have a factory selected component that would go in. And obviously that requires a factory. You can't do that when you're producing kits. So there are differences in that regard, 2 or 3 places. There are places where Heathkit made a mistake. For example, they omitted the ground connection to the comparator, which is necessary, and Weston showed it. And when I looked at this, I said, how are they getting the output to be ground referenced if they don't have a ground connection? Couple places where there's slight component differences and things, but essentially it's the same circuit. You basically have your analog front end here. This area here is the analog part of the A to D converter. This area down here is the AC converter for AC volts or AC milliamps, and it has its own front end with its own range selectors, so it doesn't use most of these. It does its own thing, and it has an op amp here for the precision rectifier circuit, which is very conventional and typical of what Heathkit used on most of their other digital multimeters, and indeed what Weston used. This is actually a little bit easier to read than the Weston one in its layout, but there's part of it that really makes it hard at the same time. There's the clock here. You always need a clock. There's a flip-flop for controlling the ramp up and ramp down to the integrator over here. And some flip-flops, there's 6 flip-flops in here in 3 ICs. And those are, about half of them are used as an extension of the counter chain that I'll talk about in a moment, and the other 3 are used as latches to latch in a particular state. And then you've got your main counter chain here. It's using a Fairchild series, which is kind of obscure. They're resistor transistor logic. Again, this is in the fairly early days of integrated circuits, so these things are very difficult to get now if you have a bad one. On the other hand, they're very simple devices, so maybe they last forever. And then you've got buffers to store the count at the select time. Then you've got decoder drivers that decode the output of the buffer storage to the outputs necessary to drive Nixie tubes, and they also have the driver circuits for those in those chips. And these chips are all part of a family. They're intended to go together in exactly this kind of circuit. They don't have any extraneous parts on or pins on them. You might normally see with other buffers, you know, quad buffers and decade counters and things, extra pins to do extra functions and make it more flexible. But these were designed as a family to do one thing and one thing only, and that is to make a series of decade counters with the associated buffering and latching and decoding and display driving. So they're all designed to have only what they need and no more. And then you've got the 4 or 3 Nixie tubes up here. You've got transistors driving 4 neon bulbs for overrange for the one that goes in the thousands place of the display. The units, tens and hundreds are done with the Nixie tubes, and then 2 neon bulbs to indicate plus or minus polarity. And then the only other thing is the power supply. And instead of wading through this, I'm going to be going to my usual hand sketches that I hope will depict things more clearly. Alright, here starts the description of the circuit operation, or the circuit theory. I'll start with the power supply. It's pretty straightforward on the front end. Just the AC line cord coming in through a chassis socket, a fuse, and one gang of the range switch, where every position except off is wired together, and that acts as the power switch. So instead of a separate power switch, it's just one gang on the range switch doing the work. And then it's applied to the normal dual primary, so having them wired in parallel like this allows 120 volt operation. If you instead wire them in series, then you can have 240 volt operation. So nothing interesting there. The bipolar supply, which is used for the analog circuits of the meter, it has a center tapped secondary winding of the transformer with 2 diodes forming a full wave rectifier. It's not a bridge, it's just a full wave rectifier, and that's possible with only 2 diodes because you've got the center tap transformer. And that's connected to, in this case, not ground, but to negative 12 volts. That is the negative 12 volt supply rail. And then the positive side here of the rectifier gets filtered with a capacitor, not a very big one, only 250 microfarads, because it has a very low load on it. And then there's this little circuit here which provides a current current limiter, and they are using that instead of a series resistor that you might normally have. And then the actual regulation, or at least something to keep the voltage approximately correct, is 2 12-volt Zehners end to end. So it's actually regulating, or at least holding. I don't think really regulation is quite right when there's no feedback, but let's just call it regulating for keeping it simple. So the 24 volts of Zener regulation is between the minus 12 volt rail and what we're now calling the plus 12 volt rail, with any additional voltage being dropped in this area. The middle of the 2 Zehners is tied to ground, establishing the middle of the 24 volt supply as ground. Therefore, what was the plus 24 volt is really 12 volts relative to ground, and what was the minus side is minus 12 volts relative to ground. So that's how the plus and minus 12 volt supplies are generated. We have a similar kind of rectifier on another winding, secondary winding. In this case, the center tap is grounded. So we have a positive voltage relative to ground here. It's got a larger filter capacitor, and then we have a Darlington series pass transistor that comes out and provides 3.5 volts. The Weston version of this meter is apparently adjusted for 3.6. And that works because the logic in here is RTL logic, and it doesn't need the strictly controlled 5 volts that, for example, TTL required, a bit later on. But still, this transistor needs to know what to do to result in 3.5 volts here. And that comes from a little Zener regulator, or a Zener reference. It's getting its source from the plus 12 volt rail. That's plus 12 volts relative to ground. And we drop most of that in this resistor, and then 4.7 volts across the Zener. That is applied to the base of the Darlington. You have to subtract 0.6 volts for each base to emitter drop, so there's 0.6 volts lost here, 0.6 volts lost here. If you take 4.7 and subtract 0.6 and 0.6 again, you end up with 3.5 volts. So that's how that gets it. There's also an additional winding. It's actually tied, one side of it's tied to this point internally in the transformer, so it comes out as a single lead. But you can think of it as being a separate, this winding just going to ground externally. So this side's there, this goes over here. It's capacitively coupled into a diode to ground, and that acts like a half wave rectifier. So what you end up with here is a pulsing voltage. Heathkit doesn't say what these transformer voltages are. I'm going to pencil those in after I measure them. But it's supposed to end up being an average 95 volts DC, and that's the high voltage source which operates the Nixie tubes and the neon bulbs in the display. That same point, just the AC, not the part that's gone through the capacitor, but just the AC, that point goes into the AC calibrate circuit, which is on the main circuit board of the meter. Has a resistor and then two diodes, one facing one way and one facing the other. And they're engaged differently depending on if a slide switch on the board is in the AC or DC position. So if it's in the DC position, then the switch is down here, and it's already shorted out, so having the switch in that position does nothing. You just have a half wave rectification through here, and then through this voltage divider to ground. The upper part's a trim pot, and you can adjust it to get a specific voltage at the test point here, which is just a pad on the circuit board. It isn't a pin or anything. But if you move the switch to AC, so you get a different voltage out here. And that's all part of the self-calibration or internal reference calibration technique that Heathkit applied. There's also another circuit which was on an auxiliary circuit board that Heathkit provided with the kit. It just had a number of resistors and a 1.35 volt mercury cell. That's a kind of, it's not really a battery, it's just a cell, but it's, because it's a mercury one, it provides a very accurate 1.35 volts. It can be used as a reference. And it also had a couple of test leads, and you'd follow the procedure for connecting the test leads to various things in the meter, or also touching the meter's test probes to 3 specially marked foils. I won't go into how all that works, but so that was the way they handled DC calibration, and AC calibration was handled with this. I also just notate here that on the Weston version of the meter, instead of having this type of reference based on a Zener for the Darlington, instead they still come off of the plus 12 volts, but they have a trim pot, and that has to be factory adjusted to get the necessary output, which is 3.6 volts in their case. That's what they wanted to have. But that's the power supply. Just a bit of a clarification on this circuit. I kind of brushed through it a moment ago, and on further reflection, it looks like what's called the Villard circuit, which is named after a French physicist, Paul Ulrich Villard. Lived in the late 19th century, early 20th century. Best known probably for discovering gamma rays in 1900. Anyway, when you've got a transformer or an AC waveform, and one side of it is applied to the capacitor like this, and the other side goes through a diode and back, in this case to ground, but that's what the other side of that winding goes to. It's supposed to be a kind of a voltage doubler, although a very poor one, and lots of distortion extremely high ripple, and so on. The idea being that on the negative, at least it's configured this way, assume that you can picture a winding of the transformer connecting from here to this point. On the negative half cycle, when current is going this way, the diode is forward biased and the capacitor is basically across the winding, so temporarily it has a charge on it. And then when you have the positive half cycle, the diode is reverse biased instead of forward biased. And now you've got the voltage on the secondary in series with whatever charge is on here, but you know, in my mind it barely works that way. And indeed, I put a scope on it, and it is sort of, it's more than a half wave. It's not really rectified in the normal sense. Certainly all of the voltage is above ground. There's no negative voltage. It's as if a large portion of the sine wave had been raised up so that almost all of it is above ground, or 0 volts, and just the bottom is clipped off. But there's more clipped off than just the forward voltage drop of the diode, at least when I measured it. And it's also a very distorted waveform, and I think that's because there's no filtering. I mean, it's hard to filter an AC signal or even a extremely high pulsing DC signal effectively, and the load on this is varied, and I think there's just a lot of noise in the circuit. So it's a very corrupted, jaggedy, misformed, you know, whatever it is, it's like 7/8 of a sine wave shape, just the bottom little curve bit clipped off. And it's not important because the only thing that's using this is the Nixie tubes and the neon bulbs, which don't care. They'll run off of AC, they'll run off of DC, etc. And I'm not actually sure if the highly pulsing nature of this, with, you know, an off period in between, might actually be advantageous for the Nixies. There is a problem you can have if you just put DC voltage on a Nixie tube, that it can get cathode poisoning. And by pulsing the power to it, you can minimize that. And so maybe this is a deliberate effort to not give it too clean of a waveform with a substantial off period, and then you have to average out these misshapen peaks with the missing minus part here. The simple formulas don't apply, and I measured it, and you'll get around, at least on mine, it's around 90 volts instead of 95, just putting a modern digital voltmeter across it. And anyway, I just thought I would elaborate on that a little bit. It's a kind of interesting subcircuit. So I don't feel like I've beaten this dog to death yet, so here's the Villard so-called doubler again, and I just feel like I have to say more about it. So let's assume that we have a transformer here with a 280 volt peak-to-peak sine wave on it, and we have this configuration. What we're going to get is actually the voltage across here. In other words, from this point to circuit ground, there must be a ground reference for these to work. It can't be, well, whatever point you're measuring from has to be called something, but in this case I'm going to call it the ground reference. The voltage across here will be exactly the same voltage as this, except it will be raised up. So if you were to look at this, 280 volts peak to peak, it would look like this. Here's 0 volts. It's an alternating signal, and it's going to go up and it's going to come down, go below 0, come back up and go. So it'll be 280 volts from peak to peak. Half of that, 140 volts from 0 to here, minus 140 volts from 0 to here. So this circuit takes that whole thing and just essentially raises it up so that it's all above ground, minus a little clipping on the bottom. That's going to happen with the diode, and so we still have roughly 280 volts peak to peak here, but it's all pulsating DC. It's not AC anymore because it doesn't go below 0 volts. It doesn't alternate its polarity, but it still looks like the same signal almost. Just a little distortion on the bottom of it. So why is this called a doubler? Well, if you're measuring from ground to this, you're only going to get like 140 volts. 0 to peak, or 140 volts peak. That's half of 280 volts peak to peak. Once it becomes DC, then you're measuring from ground only to the top, but it's the same height, so now it's 280 volts from ground to the peak. So it seems to have doubled the voltage, even though the peak to peak is still essentially the same thing. And if you were to average this, if it was purely sinusoidal, that would be very easy, but you get distortions in this, one of which, of course, is trimming off the bottom. So it's not quite that simple. And a circuit like this, because it's capacitively coupled, it can't handle much of a load. It has to go into very high impedance loads. If you have much more of a draw on it from the load, then you start getting all sorts of other distortions in here. And therefore, the simple formula for converting a peak-to-peak signal that's a pure sinusoidal signal to an equivalent average voltage DC is a nightmare, and you pretty much just have to measure it to see what it comes out to. On the Heathkit IM-102, this is actually 280 volts coming off the transformer. I measured it. That's 280 volts peak to peak viewed on an oscilloscope, and it averages to 95 volts DC. If you just stick a regular high impedance voltmeter, it has to be a high impedance voltmeter, so a modern digital multimeter or something like that, it would show you an average voltage of only 95 volts. There's a lot of space between these that is not the peak, and so it averages out. And this, by the way, was on an operating circuit in the IM-102, so it is a loaded circuit that averages to 95 volts DC. It would be higher than that if it didn't have a load on it. But that's how the 95 volt DC high voltage supply is generated and why it ends up that way. Now, just to take this a little further, often the Villard doubler, again redrawn here with the ground reference, when you want to have a more normal DC voltage, a steady DC voltage, instead of a highly pulsating DC voltage, you can add a simple diode capacitor peak detector across it, across the output of the Villard doubler. So this is the peak detector. So now it only looks at the highest voltage that you get here and stores that in the capacitor. So if you do this, now you have a DC voltage which is approximately equal to the peak-to-peak voltage of the transformer secondary. And that can make it more useful, and I already said that I think probably the reason Weston, and then by copying Heathkit, also probably did not put the peak detector on here because they probably wanted this to be a highly pulsating signal for the health of the Nixie tubes. So now that we've got that, you can redraw that, and it often is redrawn. This same thing, the Villard doubler with a peak detector, gets redrawn like this. It's the same circuit, but the diodes are going at angles. So it looks a little funny, but it's the same exact thing. Oh, I should have mentioned that the Villard doubler with a peak detector is called a Greinocher doubler. Now, if you start drawing it like this, and you do it like this if you're going to add stages to it, this is one stage of a Greinocher doubler, and if you start duplicating it over and over, it starts getting called a Cockcroft-Walton cascade, only one stage of which is the Greinocher doubler. If you, and again, you'd be measuring from this point, this is the output, back to ground, and you'd have 280 volts DC, approximately, a little bit less because of diode drops, and some other inefficiencies. And again, this is assuming no load to speak of, a very high impedance load, 280 volts DC, if this is 280 volts peak to peak. Now if you start doubling that up, for example, if you do this, this is a configuration that you often see. This is two stages of the Cockcroft-Walton cascade, and every time you add another one, the output voltage is the transformer peak-to-peak voltage added on to the output of the previous stage. So this takes 280 volt peak-to-peak, gives you 280 volts DC, in other words, from ground to this point. You add another stage, you add another 280 volts to it, so now you're up to 560 volts. If you added another stage, it wouldn't double this. Instead, it would just add another 280 volts onto it, and you could keep going. But again, as soon as you put any load on this, other than the, a very high impedance one, the voltage is going to sag, the waveform gets squirrely, there's a lot more ripple and noise. You don't use this for the kind of circuits that care. You might use this for, again, something very low current, like a Nixie tube or something, and some other high voltage applications where the voltage is important, current is not, and current is minuscule. Anyway, I just thought I would take that little digression to go into that because I think it's an interesting and not well covered topic. Alright, my first sketch is the DC voltage front end. So this is how DC voltages are scaled for presentation to the analog to digital converter. Now on this particular meter, the analog to digital converter has a built-in scaling of either 0 to 2 volts, that's plus or minus 0 to 2 volts full scale, or plus or minus 0.2 volts, that's 0.2 volts, so 1/10. And the A to D shifts gears, so to speak, between those two ranges depending on which range the operator has selected on the front panel. I'm not really sure why they did it this way. Maybe it saves a few resistors in the scaling or something. Well, and certainly Weston instigated this and Heathkit just copied it. Anyway, so the volt ohm jack is where the voltage input is applied. Common goes right to circuit ground. We have one gang of the range switch in 1000, which you really have to think of as 2000 volt. It's just that due to maximum voltage limitations of the circuit, you can only go up to 1000 volts on what would otherwise be a 2000 volt scale. And then you've got the 200 volt scale, and they're tied together here along with the 20 volt scale. So all three of those have no special treatment. They're all treated the same way here. And likewise, the 2 volt and the 200 millivolt are treated the same. In the case of 1000 volt 220, it's applied to the top of this precision hybrid voltage divider. This is a not a bunch of discrete resistors, it's a single block of resistors. And if you add it all up, it comes to 10 mega ohms, and that's a common digital meter input impedance. So that whole thing is dropped across the whole set of resistors, and then in any of the voltage ranges, that bottom of the voltage divider is tied back through the switch to ground. So essentially we put all these resistors across the input terminals regardless of range. Well, that's not quite true. Only in the 1220 volt do we put the entire set of resistors across. In the 2 volt and 200 millivolt, we go completely around the voltage divider, and that's because 2 volt, you just turn the A to D converter to its 2 volt range, and you don't need to pre-scale it. Likewise, 200 millivolt range, the A to D converter just scales itself to the 0.2 volt expectation. So that's why these two ranges go around. And everything else is just treated the same way here. It's dropped across the big thing, the big resistor divider. If we're in the 1000 volt range, it's tapped off here. If you're in the 200 or 20 volt, it's tapped off one step higher. And again, if it's in the 2 volt or 200 millivolt range, it just goes right through and on. There's an additional bit of isolation from the DC volt / ohm switch, and that would be closed in that function. There's a small capacitor, 0.22 microfarads, which provides a little input stabilization. There are 2 PNP resistors wired up as Zener diodes, back to back, if you will. And that limits the voltage at this point within a plus or minus 7 volt span. So no matter what you apply out here, this is going to clamp it to no more than plus 7 volts or minus 7 volts. And everything downstream is able to handle that range, certainly without damage. If you do have this thing suddenly act as a short circuit, you have to have somewhere to drop the voltage that's being applied, and that's why even in the ranges where we're skipping the resistor attenuator, 2 volts and 200 millivolts, there's still this 100k ohm resistor. It's a wire wound. I forget what the wattage is, but it's substantial enough that this absorbs any abuse when the clamping is going on here. And of course, if you're in the other ranges, then these resistors absorb the abuse. Breaking it down here, if you're in the 1000 volt range, you essentially end up with a 9.99 meg resistor. That's these all added together, with a 9998 ohm resistor on the bottom, and then a 90k resistor, which has nothing to do with attenuation. It's just part of the resistor network. And out of that you get a 0 to 1 volt signal. Again, it would be a 0 to 2 volt signal if we allow this to go all the way up to 2000 volts. If you're in the 200 volt or 20 volt range, you end up with 9.9 megs. We've chopped a little bit off of here, and we've got 99.998k here. So this was 9.998k, and now we've gone up by an order of magnitude. And if you're putting 200 volts up here, you'd get 0 to 2 volts out. If you're putting 20 volts here, you'd get 0.2 volts. And once again, the A to D converter shifts gears to expect one of those two ranges. And if you're in the 2 volt or 200 millivolt range, like already described, it just goes straight through as 2 volts or 200 millivolts. And that's all there is to the DC voltage front end circuit. So let's look at AC volts, the AC voltage front end. Once again, we use the same terminals, and I should have mentioned before that when you're measuring volts, there is no fuse protection. It doesn't really need it because the input is such high impedance. you're not going to blow anything up by putting even pretty high voltages on it, even though technically it's limited to no more than 1,000 volts. Because we're monitoring AC now, the first thing we see is a series capacitor that blocks any DC component of the signal, so we're just looking at the AC part. And now we go to the circuit that is almost exclusively on the smaller analog to digital converter circuit board instead of the main board. It has its own gangs of the range switch, and 1,220 volts are handled one way, and 200 or 2 and 200 millivolts are handled the other way. There's a separate resistor divider, not the same one as used for DC volts, and that's because it has compensation. It's not just AC at 60 Hertz being measured here. It can go up to a fairly high frequency, and you need to do little things to compensate for that. So there's all these either fixed or trim capacitors shunting out the resistors in this divider, and they all get tweaked appropriately for best response. And then there's another gang, the range switch, which again the goal is to get it down to either a 0 to 2 volt or 0 to 0.2 volt. That's 200 millivolts. And then we come out of there and we have clamping diodes. That's just limiting the voltage. And because these diodes will start conducting at approximately 0.6 volts, even though they're going to plus 12 volts and minus 12 volt power supply rails, once they start conducting, it's a little bit less because of the voltage drop, but it's keeping the voltage range here within the range that all the analog circuitry is powered from. We have a classic circuit here. This is a source follower. It's an FET, which provides a very high input impedance to all this circuitry, and that allows the resistance values to be fairly high here. And then the output is very low impedance, and the addition of this transistor just helps it perform better. I won't go into the weeds on that. Let's see, so then we come out of that and we go back through the range switch again. There's a little trick going on here where the resistance going into the precision rectifier circuit is adjusted. You can have a 90K and a 10K in series, which gives you 100K, or you can just have the 10K, so an order of magnitude different. The 90K in some ranges is shorted out by another gang of the range switch as needed. So now we come into the main part of the precision rectifier or AC converter circuit. Again, this is a classic circuit. It's the so-called precision rectifier. We once again make sure we have stripped out any DC component of the signal by passing it through a capacitor, and we present it to an inverting op-amp amplifier with the plus input grounded. So that couldn't be any simpler. You always want to provide a DC feedback path on these, so that's what these resistors are doing. And the middle of it's got back-to-back capacitors because it's handling AC to ground. And then the output is once again passed through back-to-back capacitors to this point. And now we are establishing our feedback. It's another negative feedback path for the AC signals. Remember, this one was the feedback path for DC. You can either have on the positive swing here, when this is positive, the signal will go this way. When it's negative, the signal will go this way through this diode. Both of them have the same value resistors, so it's treated exactly the same whether it's positive or negative part of the AC signal. And then they're joined on this side, and these act like the top of a voltage divider. This acts as the bottom of a voltage divider. And this one is adjustable. This is the AC adjust for AC calibration. You have divided this down by a voltage divider, and then you take the result of that and feed that back around to the negative input, so you've got your feedback. And because the op-amp is always trying to make sure that its inputs match, the output will drive the output, or the output here will drive higher than it is trying to get back to here, because you're going to have the voltage drop in these diodes. So you get a little bit less out here than you should have, and because of the feedback, it detects that and boosts the output here to compensate for the voltage drop in the diodes, but you're still getting the rectification. Only positive signals appear here, negative signals appear here. Since we're only interested in positive output from here, the circuit only continues from the plus instead of the minus. So why even bother with the negative? Well, if you didn't have this, then the whole AC feedback path would be non-existent for half the wave. And that makes for a circuit with stability issues. So providing an identical feedback path for the negative half the wave keeps this thing happy all of the time. So then we have a 3-stage filter to get it nice and smooth. It's a low-pass filter, so any higher bits of stuff that getting higher frequency bits of signal that might get through here are filtered out, and you get a nice stable DC signal, which is proportional to the average of the AC voltage. We pass through a coupling switch, part of the function switch, and then we're back into the same exact circuit we had for DC volts, with a small filter cap and the back-to-back transistors acting like back-to-back Zehners and clamping the voltage. And that's all there is to the AC voltage front end. Now here's the DC current, or DC milliamps front end. So we have a different jack for this. It's the milliamp jack, and the current under test comes in the milliamp jack, goes through the meter, and exits via the COM jack and goes on its merry way. Here we are presented with a 3 amp fuse. The meter can measure up to essentially 2 amps, but the fuse is a little higher than that, so you don't have it too close to the measurement range. If you put a 2 amp fuse in there, it might blow as a nuisance instead of blowing when there's really a true overload, so it's set for 3 amps. The first thing we do is run that current through another part of the range switch, and you've got a bunch of resistors in series. These are shunts. Each one's an order of magnitude different. 900 ohms, 90, 9, 0.9, 0.1. So these always end up at 1K, so a maximum resistance of 1K ohms. And then the current continues back out and out the meter. So you're running the current under test through all of these resistors and back out. Except sometimes you're not running it through all the resistors. Certainly if the switch is in the 200 microamp range, then you're running it through all the resistors. But if you're, say, passing 200 milliamps through this instead of 200 microamps, then the switch contact would be down here, and the current is taking the shorter path and going through less resistance before it goes out. But if you do the math and multiply the current by the resistance, you end up with the same kind of voltages you would get if you were in DC volts. So all ranges except for the 1000 milliamp, which is 1 amp range, are full scale to the A to D of 0.2 volts. But in the 1000 milliamp range, it works out where you're getting 0.1. And of course, that's not due to any functionality of the circuit. It's simply because you're not going up to 2 amps. If you were going up to 2 amps, it would be the same as this. We have exactly the same filtering and clamping here. What if you apply a whole lot of current here very quickly and the fuse hasn't blown yet? You need some sort of protection so you don't smoke these resistors or do some other damage. Once the signal gets to here, it'll be clamped by this if it needs to, but there's a protection circuit here. 2 diodes facing that way and 2 diodes facing that way. Let's take a look at the one in the positive direction. So we have these 2 diodes. This is plus 12 volt going through a resistor, through this diode, and back out. So this diode's always kept conducting. It's not ever not on, but it still can only conduct in one direction. It can't conduct the other way. But all it is for our purposes is a 0.6 volt drop. So that voltage applies to here. This is essentially a node that's 0.6 volts all the time. And therefore the voltage here only needs to get up to 0.6 volts plus 0.6 volts. It needs to be 0.6 volts higher than this voltage to forward bias the diode and start conducting, but this point is already 0.6 volts. So those two together is 1.2 volts. So once the voltage here gets to be 1.2 volt, then this will start conducting. The maximum voltage you would expect to see across these resistors is 0.2 volts, so this is actually pretty generous. And likewise for negative, it's just the same thing, but it's going to minus 12 volts and the diodes point in the other direction. Here's the AC current front end. It's exactly the same up front. It still has the same clamping. It uses the same shunt resistors. But the output, which is again a voltage, we've converted current to voltage by running the current through resistors across which we can get a voltage drop. But here we enter the AC converter circuit board through a different input than we would if we were measuring AC volts. So here we have a current adjust potentiometer, another resistor, a couple of series capacitors. By their orientation they make it into a non-polarized capacitor, and then we come around, we go straight into the precision rectifier. We bypass the normal attenuators that are used in the AC volts circuit because we don't need them. You don't need input attenuation for measuring current, and indeed we have our own set of resistors in the form of these shunts tied to the range switch that sort of replaces the resistor voltage dividers used for voltage measurements. That's why we have to come into this differently, so we don't go through those other things. But otherwise everything that happens with the precision rectifier is the same. And this is just illustrating how the voltage signal would usually get in, but here it's just tied to ground so it doesn't cause any problems. And then you exit the same way through the low-pass filter, the filter cap here, the clamping, and it's exactly the same thing as everything else we've looked at up to this point. Okay, now for the resistance or ohms front-end circuit. This is a weird circuit and I had trouble figuring it out. I was not successful in my own circuit study to completely understand how it worked. There were some areas that just did not seem right, and the Heathkit description made a dog's breakfast of it. It just made it confusing, more so than it already was. And the Weston one was a little better, but still left things in an unresolved state as far as I was concerned. is like everything makes sense up to a certain point, and then there's a leap, and it's like, well, how did it get from here to there? And I was actually on a plane trip, and trying to make myself go to sleep, I was thinking about the circuit. And I don't know if it's like the dreamlike state or something, but all of a sudden it hit me how it worked. Anyway, so one of the common ways of reading a resistance in a multimeter is to pass a constant current through the resistor under test, and then measure the voltage drop across it, which will be proportional to the resistance. That works great, if you've got a constant current source. And there are a lot of variations on that. There are also ratiometric circuits where you do not have a constant current, but you pass a current through a known precision resistor, and then also the same current goes through the resistor under test. You measure the voltage drop across the known resistor, the voltage drop across the unknown resistor, and you take the ratio of those two, and then the ratio is the value of the resistance under test. That's the way it was actually done on a lot of the handheld multimeters. It's a minimum parts count kind of solution, and since the ICs that are at the heart of so many of the handheld digital multimeters have a ratiometric input, it's just a no-brainer that you're going to do it that way. But this is the only time I've ever seen it done this way, and I'm guessing it's not because of Heathkit, it's because they had inherited the brainstorm of somebody at Weston who did the 1240 meter. Some of the things they're doing differently here is they've arranged it so there isn't any calibration except for the highest resistance range, which does have. They're also taking into account the inherent resistance of the fuse that's in this circuit, and they're making a great big feedback loop, like a negative feedback loop. I'll try to go through it here and see if I can make it make sense. So because it's a feedback loop, you can start at any place in the loop and say, well, this is the value that should be here, and then follow it all the way back around, and it should still make sense when it comes back to the start. So just geographically speaking, we have a small constant current source here. We have an op-amp with negative feedback. We have a bunch of resistors in series. These are the same resistors that are used as the precision resistors for attenuating the volts inputs, at least the DC volts inputs. We're just using it differently here. Then after the output of the IC here goes through these resistors, or some of them, it goes through the fuse, out to the volt ohms jack, through the resistor under test, which is RX, and back to ground. So you have a current path driving this. So far so good. The voltage drop across RX is called VRX, and that is proportional to the resistor, of course. Then we take that out here, we go through another gang of the range switch, but this is just for switching purposes. It doesn't change anything from range to range. It's the same on all ranges. And then part of the function switch, and then we're going straight into the front end of the analog to digital converter, just like we do for everything else. Got the filter cap, got the clamping transistors that act like back-to-back Zehners, and then we go into the front of the AD. Now, I've sort of dashed in that circuit. We haven't gotten to that circuit yet, but it does have an IC op-amp acting as an integrator. That's the core of the analog to digital converter. And
that op amp is doing its thing all the time, regardless of which range you're in. That involves in integrating up and integrating down, because it's, after all, an integrator. So it's busily doing its thing with a capacitive feedback and so on. So we have to necessarily apply that signal from here to the plus input of the IC. The negative input is tied up with the integration feedback loop, and the output here is a ramp that goes up and down. And you're thinking, well, why are we doing that? That seems wrong. I mean, obviously you have to put this signal into the integrator in order to measure it. But the part that was choking me up initially was, then why is there a connection from the minus input of this op amp back to the plus input of this op amp? Why is that there? And I was almost thinking I had it, but it still didn't make sense to me. Why are they picking the this input from this input? And what I was forgetting was that in op amp with negative feedback, assuming everything's working correctly, it doesn't matter what the op amp is doing, it's always working to have its output be such that, with the feedback, that the two inputs match in their voltage. In other words, the same voltage at each input. So if we have VRX here, and I should have penciled that in, I said it here, but I'll put it here again, VRX. If you have VRX here, then it must have VRX up here too. So I'm going to pencil that in. It is also VRX. Okay, well, it's not the same VRX. It's a copy of VRX created from the output of the op amp. And it's a brain teaser, because you're thinking, well, this is going up and down. Isn't this going up and down? Well, not in this configuration. You've got this capacitor here, and the behavior of the capacitor in this type of circuit, it's just doing what it needs to do, and this is doing what it needs to do in order to result in the same thing here as there is here. So we'll just take it as a truth that you've got VRX here. VRX is fed back to here, and it acts as an offset. When you have an IC op amp with negative feedback and you inject another voltage into the plus input instead of just having it grounded, it acts as an offset. So the op amp will have it as its output whatever voltage is here, amplified accordingly, and then adding the offset voltage to it. So let's look at this part. So there's a little constant current source here. It's actually drawing current out of this circuit, so it's a constant current sink actually. You have between ground and minus 12 volts a resistor and a Zener diode, and that produces a reference voltage here. And that is applied to the base here. And if you have the base of a transistor in this configuration held at a constant voltage, then the current here will be constant. And you can vary it by putting a different resistor value from the emitter to the voltage here. So this is where you can tweak it, and this is indeed called the 20K adjust, but it works on all the ranges. We are drawing some current, and it's actually 1 milliamp. You adjust this for 1 milliamp. And so 1 milliamp is coming into here. Well, we know we can't put current into or out of an op amp input because the impedance is so high. I mean, there's a minuscule amount, but it's negligible. And therefore, that 1 milliamp must be coming this way. It's the only other way you could get there. And therefore, there's 1 milliamp times 1K is 1 volt. So there's 1 volt across this, and that means that it's going to try to have 1 volt here. But because of this offset voltage, VRX is added to the 1 volt. So the output here is always VRX plus 1 volt. The plus 1 volt part comes from all of this. So far so good. So now we're applying VRX plus 1 volt to the top of this, and regardless of the range selection here, this will always have a voltage drop across it, and keeping in mind that this is the top half of a resistor voltage divider and RX is the bottom half of the resistor voltage divider, and this has already got RX across it, so we have to take the VRX plus 1 volt that we know is up here and subtract the VRX that we know is down here, which means what? It means there's always 1 volt across this, or at least whichever part of it is currently selected according to the ohms range. And by the way, that 1 volt that's dropped includes the tiny amount of voltage that's dropped across the fuse. So that's included in this. And that's why this resistor here, which should be 1K, is actually 996.5 ohms, and that's specifically to offset the resistor here, because if you add the typical resistance of this fuse to this, it becomes 1K. Okay, so we know you've got 1 volt across here. Let's say we're in the 200 volt or the 200 ohm position, so the connection is here, and this is 996.5 ohms, so we have 1 volt across that combined with the few ohms that are here. We'll just say that's essentially a 1K resistor between the two of them. 1 volt across 1K is 1 milliamp. So we know we have 1 milliamp flowing through here. And that means that there's 1 milliamp flowing through here because current can't flow this way. It's all going into this ultra high input impedance of this. It has no other place to go. So the current must be flowing in this direction. Therefore you have 1 milliamp also through RX. Let's say that RX is 200 ohms, the full scale value for the range. 1 milliamp times 200 ohms equals 0.2 volts. So we've got a VRX of 0.2 volts, and we know that the analog to digital converter either expects 0.2 volts at full scale or 2 volts depending on other factors, what mode the integrator is in or the A to D converter is in. So everything adds up, everything makes sense, and it's still a precision current going through this. You're selecting how much current needs to flow in order to get the proper 1 volt dropped by the resistor or resistors here. It takes into account the voltage drop of the fuse. It results in a known current going through here. You might say, well, isn't that enough? Why do you need this feedback? And the only reason I can see for them doing it is they wanted to put it in a feedback loop and thereby dial out some other variations of things that might go on in here by putting them in a feedback loop. So that's about as much explanation as I can give for that, but obviously it works, and when you look at it this way as I described it, I think it makes sense. A subtlety of this ohms measurement front-end circuit is that the current must necessarily change through this path depending on the range. And that's because we know there must be a 1 volt dropped across, however much of this is actually in the circuit according to the switch, and the resistance values therefore change. If the voltage is constant and the resistance is changing, then the current must be changing. We also know that
whatever current flows through this section must also be flowing through Rx. And here's a little table of the Ohm's test current, or the current through Rx, according to the range, according to Z, or the R of Z101, in other words, how much of this stack of resistors are actually in the circuit depending on the selected range, plus RF, the resistance of the fuse, which is negligible in everything except the lowest couple ranges. So we don't have a straightforward 1K resistor here, like I already said. It is 1K if we add the resistance of the fuse. So I'm calling it 1K here. Then the next range is 10K. For both the 20K and the 200K, it's 100K. For 2 megs, it's somewhere in the ballpark of 990K. And for 20 megs, it's adjustable somewhere between 9 meg and 10 megs. Using the trim pot here, that's the 20 meg adjust. Why are these last two ranges using a different resistor than you think they would have? Why isn't this 1 meg and why is it 990K instead? Why isn't this just 10 meg instead of somewhere between 9 meg and 10 meg? And that's because the currents are starting to get really small here. You're down to 1 microamp, 100 nanoamps. And that's current that's coming out of here. And we always say, well, we know we're stealing 1 milliamp to go this way, and the other current must be going this way. And we say no current can go into or out of this negative input due to the high impedance. But when we start getting up into the very low currents in the higher ranges here, and the very high resistances out here, they start becoming significant when compared to the high impedance here, to the point where a tiny amount of current is essentially going in there. Heathkit's manual calls it the bias current, but it has to do with the interaction between the high impedances out here and the impedance here. So they're compensating by adjusting the resistances down a little bit here, so you still get the right amount of current going through here. It's like, well, some current's going to be trying to sneak out this way that shouldn't be, so let's lower the resistance a little bit here so there's more reason for a little bit more to be going this direction. I don't even know if they calculated that back at Weston when they devised the circuit, or if they just found it out by accident and had to adjust it empirically. Anyway, that's the reason those are lower than you might think they should be. That was something that had me scratching my head, and I finally kind of thought, oh, could it be for that reason? And then I checked the Weston manual circuit description, and they actually kind of hinted at it, so I'm sure that's what's going on there. Okay, for probably the most difficult part of the circuit, this is the analog to digital converter, which is also the input amplifier and includes the integrator. This implements one of the forms of a dual slope integrator analog to digital converter. And there's various ways of doing this, but it's an improvement over the old single slope integration analog to digital converter. Matter of fact, the other contemporaneous Heathkit early DMMs all use the single slope, but this is more accurate. Has more resolution. It needs to have the extra complexity to minimize drift and inaccuracy and temperature susceptibility and things like that. It's too complicated to go into all the weeds on why the dual slope is used, but invariably you have a ramp voltage in the integrator. It ramps down and then it ramps up and it ramps down, it ramps up, repeat, repeat, repeat. This probably goes on indefinitely while the meter's turned on. There will be one way of doing it is to have a constant current source
or a constant voltage applied to the integrator and let it ramp up for a fixed period of time, and it'll get to some voltage, which in itself is not important, but all the variables in the circuit are part of the math that calculates or determines how far the ramp gets at a given moment. And then the circuit flips and it configures the integrator to ramp down starting from that point, whatever it is, and now it's paying attention to how long it takes to ramp down, and the input voltage is added to the mix of factors that stipulate this. And so essentially when you're ramping up, for example, you are sort of taking a snapshot of all the variables in the circuit, component values, you know, how things may currently be, what their values are according to temperature at the moment, things like that, and it gives you a baseline, and then you take the actual measurement as you're ramping down from that reference point that's just been established, you know, a fraction of a second earlier. And that's about all I want to say about that, except the Weston version, and hence this Heathkit version, it doesn't use a fixed voltage into the DMM. It uses the ramp up occurs based on the input voltage, so it's almost turning the whole thing up on its head, and then it ramps down according to a reference. So it's still accomplishing the same thing, it's just sort of using the ramp up and the ramp down in the opposite way from what's probably the textbook version. So here's the IC integrator. It's just like what I showed in dashed lines when I was talking about the resistance or ohm circuit. The V-in from the front end circuits comes into the plus input, and that's the only thing that goes there. Then you've got your capacitor wrapping around to the minus input. They also have a 100K resistor here, which although it's 100K, it's negligible compared to the very high input impedance of the op amp, so you can pretend like it's not there for this discussion. And therefore you have an integrator. Well, normally the integrator would be in this configuration, V in here, capacitor, and then a resistor to ground. So we have to have something acting as the resistor to ground. We're treating this one as negligible because the feedback comes to this side of this resistor, not this side. Now I'm going to jump down to this same sketch I started with. So you've got a ramp up, ramp down going on, and part of what influences that and where the reference is comes from a couple of precision constant current sources. One's actually a current source, one's a current sink. They're both configured to source or sink 400 microamps, and they're called plus Iref, in other words the positive current reference, and minus Iref, and those are controlled by logic. And then the output of the integrator goes into a comparator, which is comparing against 0 volts by being connected to ground. So this baseline here is 0 volts. There, I penciled that in. So it's always ramping down to 0 volts, then ramping up, ramping down to 0 volts. So it's important to detect when the ramp gets to 0 volts, and that's what this does. It's technically a zero crossing because you can't just touch 0 volts. You have to go ever so slightly, you know, past it, just enough for the IC to detect it, and then say, oh, one's bigger than the other, or vice versa. And it does that whether this point is high or low. The comparator IC that's used for this has a ground reference, so instead of the output flipping between, say, V plus and V minus, plus 12 volts or minus 12 volts, which it does have, its output goes between the ground reference, which is connected here, and the V+. So here is the second op amp acting as it's actually a comparator op amp. It's not going to function as a regular op amp. The output of the integrator is divided in half by two resistors and a voltage divider, a minuscule amount of filtering, and then applied to the minus input. The plus input's going to ground because we're trying to compare against 0 volts. And then you've got a logic signal coming out. So I'd said that you need to have a resistor going to ground for this type of configuration to work, and that's what this whole hairy thing does. And this resistor is what controls the gain, because in addition to this being an integrator, it's also the front-end amplifier after all the front-end circuitry. And so we have to be able to calculate gain. And the value of this cluster of things that acts as a glorified version of this dictates that. So what do we have? We have 17.8K resistor and a 1K resistor, which would be set to some particular setting during calibration. And I wrote a note here saying the 2-volt full-scale trim pot is adjusted to 200 ohms so that this resistor and this resistor added together equal 18K. That 18K plus the 2K here is 20K, and that is essentially the value of R, meaning this resistor down here. Then we have a little low impedance circuit here. This is your zero control. Where does the meter circuit think 0 volts is? And more importantly, it also allows dialing out any inherent DC offset that might creep into this circuit. That's its primary function. So we have a 5K resistor with essentially a 5K resistor on either side going to plus 12 volts, minus 12 volts. And with these resistor values, it ends up being 8 millivolts plus 8 millivolts minus. So you can move this pot between minus 8 millivolts and plus 8 millivolts. That goes through a 2K resistor and then a 10 ohm resistor to ground. So it establishes a very low impedance source for this, and it needs to be in order for it to act like ground. It can't have anything going on here wiggling this thing around because this has too high of an impedance. It must, for all practical purposes, to the rest of this circuit act like it actually is ground, and having it have an impedance of 10 ohms is close enough. So we know that the integrator has to have a sensitivity of either 0.2 volts full scale or 2 volts full scale. And changing the value of R here by order of magnitude is what accomplishes that. And so in the milliamp range, you are using a set of shunts to come up with the input voltage. And if you are in DC milliamps, you short out this part of the resistor, leaving only 2K. So by shorting this out, it changes it from a 20K R value to a 2K R value. Likewise, if you're in DC volts or ohms, the switch from one resistance here to another happens on the 20 volt range, the 200 millivolt range, the 200 ohm range, the 2K range, and the 20K range, but not on the other ranges. And if we went back and looked at the front end circuits again, we would see that this corresponds to that. If the front end circuit is assuming in its attenuation or its shunting or whatever that the output of the front end will be 0.2 volts full scale, then correspondingly here we will configure this resistance value to make this a 0.2 volt. What's expecting 0.2 volts is full scale, and the same thing for 2 volts. So that's what that's all about. It looks complicated, but once you know what it's doing, it makes sense. And we know from this that we still need to have a couple of precision 400 microamp source and sink circuits, and that's what's going on here. I'll look at the source one first. The sink is just a mirror image of it. We have these dual transistor packages. So 2 transistors that are well matched and put together in the same package. So their thermal characteristics track each other. We use plus 12 volts through a 6.2 volt temperature compensated Zener diode, and then a resistor to ground. So you establish a point here that's 6.2 volts less than the 12 volts. And that causes a certain amount of current to flow. And that influences, because in this arrangement, the 2 transistors tend to track. So you've established on this side a particular voltage on the emitter, and that's going to control how much current goes through the other transistor, although you can tweak it with a resistor here. So there's a positive range trim pot and then a resistor, and then you go through it, and you should have 400 microamps coming out. And then that goes directly into the minus input of the integrator circuit. And then again, the mirror image, so current can flow out of that and go the other direction and be a 400 microamp sink. By choking the bases of these 2 transistors, dragging them to ground, you can turn this current source off, well, on and off. If you don't short it to ground, then it's working. So there's logic that determines when you need this, and it turns this transistor on and off, which in turn allows this one to work or not. Same thing happens for the other side, the negative range. And I want to mention here, how does this thing work if you have a negative input voltage? After all, this multimeter can accept negative inputs. Well, if you put a negative input in at V in, it gets through the front end circuits and ends up being negative, and that would happen on volts or milliamps. If you've got the milliamps going the other way, you get a negative voltage. And the same thing happens, except the ramps are on the other side of ground. So when it's in the so-called ramp up mode, it's actually ramping up, but in the direction opposite from 0 volts. So it would be going down here, and then this part of it would be going back this way. It's all under control of a timing cycle in the logic, and the logic keeps track of when things happen, and by doing that, it's able to determine whether you have the ramp in the positive realm or if it's in the negative realm. It changes when the zero crossing happens, and from that it's able to figure out whether you're dealing with positive or negative, and that wraps back through the logic and determines when we're trying to ramp, when we're trying to use the constant current source to dictate the ramp, which one of these do we need to have it going in the right direction? Do we need to be sourcing current to make it happen? Do we need to be sinking current to make it happen? So that's what's going on there. Let's see. Another thing that happens with this, and I chose to put it on this sketch, the logic normally figures out when there's an overrange by analyzing what's going on with the output of the comparator, when it changes and where that happens in relation to the overall time cycle. It can figure out if you've got an overrange, and also looking at the count. But under certain conditions, that may not turn on the overrange light bulb or the overrange lamp. So there's this little back door thing. Normally you would have the overrange neon bulb up here controlled by this transistor to ground, and the logic would be telling it to turn on the transistor and hence turn on the lamp. But assuming this isn't doing its job at the moment for some of those eventualities, if this point gets too high, then these two transistors are connected as a zener, and it'll cause the zener, whichever one's pointing in the right direction, to start conducting, and that goes through this diode. It reverse biases this one, it starts going through this diode, and even though this might be low and not turning the transistor on, now we're turning it on by a signal going this way. If the voltage here is too low during negative readings, then this one will start conducting, and it pulls this point lower than it would be normally, so it pulls it into the negative region, and therefore no matter what the base is doing, the emitter is lower, and therefore it starts conducting, and either way it turns the lamp on. So that's what that little circuit is for. It's a backup. I made a block diagram here of the logic circuit. It's too complicated to try to explain in detail in a video like this. The video will go on for many hours, but I think I can provide a bit of a snapshot of how it works, a simplified version, but all of this is accurate. So here again is our integrator. Here are the two current sources. Here's a block of logic that decides which one of those should be on and when. Here's your comparator. The output of the comparator is applied to a bit of logic here, which I've just shown as a box. It's essentially an NOR gate, a logic gate, and also some RC networks. And an inverted version of the comparator output's also applied to that. And from that we either have a signal here or we don't, and that wraps around and gets used over in this logic. Those two signals, the non-inverted and the inverted versions, also feed back into the logic controlling the current source and sink. We have a 40 kilohertz clock oscillator comprised of a couple of NOR gates and some RC to stipulate how fast it runs. And this is a good point that I forgot to mention when talking about the dual slope. Inherently, by the dual slope method, since it's essentially kind of taking a ratio of two different things, measuring different things on the up slope of the ramp and the down slope, if you do the math on it, if you write a mathematical model for what's happening in the up ramp and the down ramp, or upslope, downslope, whatever you want to call it, and then combine those formulas into a single formula, some variables drop out of the formula. They get canceled out, and the simpler formulas for each part involve the R and the C in the integrator, and also the frequency or the time period, rather, not the frequency, but the time period that's allowed for one of the ramps to occur. Those things drop out of the equation, and therefore it doesn't really matter what the value of C is. It doesn't matter exactly what the value of R is, at least for accuracy. And likewise, it's fairly tolerant of exactly what the time period is, as long as that's not, moving around quickly. As long as within a particular cycle of measurement the variables don't change. The resistance doesn't change, the capacitance doesn't change, the clock doesn't change its frequency, and the clock frequency, of course, dictates the time periods that the integrator works with. So essentially these variables that would normally make a integrating A to D converter less than as stable as you might wish tend to drop out of the equations, and it becomes very tolerant of variations in clock frequency, drift of the capacitor, the resistor, things like that, either over time or over variations in temperature and so on. That's one of the big advantages of the dual slope A to D. Anyway, so we have the clock here, and it feeds into a decimal counter. So this counts up to 10 and then resets and counts up to 10, resets, and so on. Every time it resets, it passes a signal on to another one, which does the same thing, passes a signal on to the third one, which does the same thing. And that results in a count where this one holds in it the value in the units value, the tens value, and the hundreds value. This meter can read up to a count, if you will, of 1,999. And so the 1,000 we haven't talked about yet, that's in the thousandths range, but the hundreds, the tens, and the units are all accomplished by these 3-decade counters. And then the output of that, when there's an overflow to the hundreds, that goes into a flip-flop, and when it's one way, you don't have a value in the thousands position. When it's the other way, you do. So this essentially acts as a divide by 2, and it starts out reset at 0, but when you get an overflow from this one, it flips it, and now it's a logical 1. And that means that now we should have a 1 in the thousands position. So again, 999 and a 1. This is backwards. The thousands is on the right. And I didn't write that in here, and I should have. I'll do that now. Okay. So you would have a 1 in the thousands position now, and then all these would have rolled over again, and they count back up to 999. And that's your maximum count. Again, it's reversed left to right here. The next time it rolls over that whole thing, now this thing flips back to 0 again, but other logic has captured that and said, okay, no, when that happens, you have overranged. You've gone beyond 1,999. So there's another flip-flop here that, I'm sorry, the divide by 2 happens here, and the actual flip-flop that captures the thousands is a separate flip-flop here. When you roll over again, this other divide by 2 here detects something else, and it's kind of interesting. When that flips over, there's a logic circuit here that detects the value of 8,000, and that's because the way this thing works out is you go way beyond the 1,999 value. After that, you don't care, but there's this overall cycle time. If I can find my sketch again. You have a ramp down, you have a ramp up. We're calling the ramp up T1, the ramp down we're calling T2, and the point between them may go back and forth, but overall from here to here must be a value T, and that is dictated by the clock. And this is called the cycle, the integrating measurement cycle, and it all happens within a count of 8,000. So the 1,999 occurs during this short part, and other stuff happens during this part, which is got to be whatever value is measured, which is either 1,999 or less than that, and that means that the rest of this must be the value of 8,000 minus that, whatever it is, but they still have to add up to 8,000 from start to finish. At a frequency of 40 kilohertz, if you're counting up to 8,000, that works out to 0.2 seconds for that to occur, which tells us that the entire integrating measurement cycle occurs 5 times a second, which is plenty fast enough. So other logic takes place in that period beyond when it's counting the initial count. So at that point we've already captured the values from the decade counters into a series of latches or storage registers, and the flip-flop here acts like the storage register for thousands. So now we don't care that the counter keeps counting up beyond 1,999. It's doing other things in establishing the value of t in the overall greater picture of things. So we've got the 8,000 count detector here. This is when we have to flip around, and there's some little RCs here for timing, and that is combined down here with the output of the zero crossing signal shaper, and ultimately there's a flip-flop here built out of 2 NOR gates, and this is what's determining whether we're in T1 or if we're in T2 based on all the other variables. And its output does several things. First off, most directly, it's the I reference enable. Once this is flipped, now we're in the ramp down portion of the cycle, and it's time to engage those I refs here. We need to start either injecting or sinking the 400 microamps from the integrator at that point in time. So the logic here already knows which direction we're going to be doing it based on the aforementioned information from down here, but it won't actually turn the selected one on until it gets that signal saying it's now time to start ramping down. So that's one thing it does. Then we go through another RC timing function. This is to generate a pulse, a very brief pulse, and that gets inverted, and that's the MSI storage. So that wraps back around here, and that is what's telling all of these storage registers to take the snapshot of what's currently in these decade counters at that split second period of time. After that, these are going to keep counting and do other stuff, and they'll be inaccurate, but at that exact moment when the flip-flop flips, then we know that the values in here are directly associated with the value we're measuring, and it's time to take the snapshot and store it in here, and then let these keep on counting and doing their other job. We also need to capture the thousands, but this needs an inverted logic to work. So there's an additional inverter here that takes that same pulse, and this is for storing the thousands value and also the overrange. So that signal comes over here, and it goes up as one of the inputs to this flip-flop, which captures the 1 being in the thousands position. It also goes up into the flip-flop for the overrange indicator, and it's in turn dictated by this second divide by 2, and so essentially if you have an overflow from the thousands position, if you have it once, it's just at the normal thousands position, and then if you have it twice, that means it's gone past 1,999. It's essentially gone to 2,000. And then this divide by 2 captures that. That gets stuck into the flip-flop, latches it in, and you get an overrange indicator. And then finally, if that one overflows with another divide by 2, that's another of the inputs to this logic, which determines if we should be ramping up or ramping down. So that's the quick tour of the logic that's really in control of everything. Okay, here is the last sketch. This is the everything else sketch. This is the high voltage Nixie and neon displays and drivers, the clock oscillator. So we've got 4 neon bulbs, and they need to be controlled. And we have the 3 Nixie tubes, and they need to be controlled. I've redrawn what was in the block diagram with more schematic detail. So these 3 decade counters and the 3 storage registers, and then I didn't talk about it, but the display decoder drivers are all redepicted here. And I think I might have already said that the meter uses a fairly ancient, as far as ICs go, series of dedicated clock counter ICs from Fairchild using RTL logic, quite an old technology. I believe it was the Apollo guidance computer, which is, you know, not too different in time period from when this was developed, using the same kind of logic. It's very robust, although it's not the, you know, it's fairly power hungry because there's resistor transistor logic. That means you've got voltage drops in all the resistances, and it's a kind of a wasteful technology in terms of power consumption. But it is, you know, a fairly simple and robust technology. Anyway, so we have our 3 decade counters here. And the clock, again, it's 2 inverters. I might have said before it was 2 NOR gates, but it's 2 inverters with capacitors crisscrossing so they feed into each other and it oscillates. You can tweak it by putting a variable resistor across this one inverter, and that's the 40 kilohertz adjust. And this oscillator can be turned on and off too under control of the logic, and it can do that by swapping this point here through a germanium diode back to the same control signal that controls these latches here. So we developed the count. Oh, I didn't draw it in. I have a mistake. I'll fix that. Alright, so we have the output of the oscillator. It goes into the clock input of the first decade counter. Then you come out of the overflow, go into the count of the next one, overflow, count of the next one. Yeah, I'd also forgotten to show the carry from the hundreds decade counter, so I penciled that in now. That goes on to the logic. And once again, I probably should have done this better. I'm going to keep fixing things until I get it closer to right. There we go. So the overflow, it actually gets conditioned by another IC, or yeah, 2 different ICs before it finally gets to the flip-flop for the thousandths position, but that's essentially where it's going. So we've got all that stuff going on. We've got the buffer storage here, or the latches, the binary data in 4 bits from each of the decade counters goes into the 4 inputs of the quad storage ICs, and those are controlled by a gate which comes again from the controlling logic. And once they've captured it, whatever they've captured gets displayed, but it's not in a format that can directly operate the Nixie tubes, so the binary outputs of the storage registers goes up into the binary inputs of the decoder driver chips, and that does 2 things. First off, these ICs convert the binary into a 1 of 10, 0 through 9, which of the parts of the Nixie tube should be lit up according to the binary value. Also, you need to be dealing with the high voltage operation of the Nixie tubes. So there's drivers in here which are designed to drive Nixie tubes, and they take care of all the circuitry, and that's able to handle the higher voltages and so on than a simpler circuit would be. So everything you need is in this one package, decoding and driving. And then you've got 10 different signals for the 0 through 9 in each digit, and there's also a decimal point on each of these. And the decimal points, I think, are actually the left decimal points. It does no good to have a decimal point on the right hand side of the units digit, for example. So I believe those are the left decimal points. So just to reiterate that the decimal points that are controlled in this circuit are the ones on the left side of the digit, not the ones on the right side of the digit. And those are controlled directly from another gang of the range switch, depending on which range you're in. Depending on the scaling, certain times you need to have it be between the least two significant digits, or one position left or one position left of that. So you might have 1.999 or 19.99 or 199.9, and in the thousands range you don't have any decimal point. Anyway, so very simple circuit. You're just providing a current path from the decimal point of 1 and only 1 at any given moment, Nixie tube, and then through a current limiting resistor to ground. So that takes care of that. The high voltage for the Nixie tubes comes from the power supply, roughly 95 volts DC. It's actually a pulsing high voltage, not a constant high voltage. Remember that from the power supply circuit, all we have is a half wave rectified sine wave with no filtering whatsoever. So it's essentially at 0 volts half the time, and then half of a sine wave shape up to around 95 volts or thereabouts. I think the 95 volts is an average. And then repeat. So it's a pulsing waveform, not a steady state DC. That's what's applied up here on the rail, and I think, again, for sanity in the future, I'm going to show that this is a pulsing half sine wave signal rather than a fixed 95 volt DC signal. Okay, so that handles that. I think we covered everything there. So let's look at the thousands indicator first, which only displays a 1 in the form of a tall, thin neon lamp that's turned on or not. There's a voltage divider off the high voltage power rail, 33K over 120K. So it just reduces the voltage a bit. Goes through the neon bulb, through a transistor to ground. And the base of that transistor is controlled by an output of a flip-flop, the one that is storing the 1000s position from the rest of the counter logic. Similarly, if we have a plus or a minus, and the plus or minus is also dictated by the logic, and that depends on whether it's detected that the ramp is negative going from ground or if the ramp is positive going from ground. As I already mentioned, it's one or the other. It detects it and then locks on either minus or plus during the entirety of that cycle. And then on the next cycle, it might decide now it needs to be the other one, but at least during one cycle it has only one of them on and it cannot change during the cycle. It's the same thing, but you don't have the voltage division here. You just have the 33K resistor, and then it goes through one of the two neon bulbs, through one of the two transistors, and now it's conditioned by another gang of the range switch. So in any of the voltage, which are also the current range positions of the switch, you need to have a path for the plus and minus, because both voltage and current readings on this meter can have a positive or a negative aspect to them. And then you also have to be in either the DC volt ohm position of the function switch or the DC milliamp position of the function switch, and finally a path to ground. If you're in any of the resistance ranges, those don't have polarity, so regardless of what the logic might otherwise be turning on here, you don't want to have either of these lamps turned on. But if you're in any of the volts or milliamps positions or functions, one or the other of these lamps will always be on. And then finally we have a very similar circuit to what we had for the thousands. This is for the overrange lamp. It does have the voltage divider. It has the transistor. Everything's pretty similar, except here we have a resistor going from the emitter to ground, where we did not have that over here. And that's for the circuit I already mentioned that has the manual override of the overrange indicator coming directly from the integrator output through that circuit I already talked about. I found another mistake. I had the diodes pointing the wrong direction on this version of it. Anyway, so that's the same thing we've already talked about. I believe the reason why these dividers are necessary is that these are smaller neon bulbs and these are larger neon bulbs here, and their specifications probably stipulate a different amount of current, or maybe a maximum voltage across them or something for best operation. Interestingly enough, on the Weston version of the meter, it doesn't have the voltage dividers. It just has a 100K resistor for everything. So I don't know if that means Heathkit was using different models of Nixie bulbs than Weston was, or if Heathkit just decided they didn't like the way Weston did it and they should refine that circuit a little bit more. Don't know. Oh, I should have mentioned that the two polarity lamps transistors are controlled from the Q and Q naught outputs of the polarity storage flip-flop. So another nuance I forgot to mention, I said that for a current path to exist for the polarity indicators, you had to be in the DC volt ohm position or the DC milliamp position. What about the AC volt or the AC milliamps? Well, then it's AC and you wouldn't have a polarity indication, so those switches are not part of this. You do not have a path when you're in resistance. You do not have a path when you're in either of the AC functions. Only the DC functions allow these polarity lamps to be illuminated. Okay, I'm in Tinkercad and I'm just throwing this thing together real quick and dirty. It's going to be made out of 4 blocks all stuck together. First block is here. 33 millimeters from front to back, 2 millimeters thick, and 65 millimeters wide. I've positioned 4 holes that loosely go around the tips of the Nixies and the one neon bulb that will be involved. Those dark areas are the negative space that'll form the holes. There's the back panel. It's only 1 millimeter thick. If it's any thicker than that, it'll hit components. And I think that's about the smallest my printer can reliably print, especially on a tall wall like this. We'll see how it turns out. I don't think it'll wander too much. I've done some thin things before. We'll see. It may be putting it to the test. Anyway, I just need to get it in position now, sitting on this plate. So now I've got the back in place, and I can verify that it is
lined up with the back of the roof here. Remember, everything's upside down here. And there's a gap there which I need to clear the neon lamp holder. So far so good. And now I've got the end plate in position and sized. Well, not in position, but sized. I just need to bring it up so it goes up against the edge of that and against the bottom of this. Alright, so that seems to be in position. I can see I've got the desired overlap with the back plate. It lines up with the front edge. And it lines up with the bottom here, but it's really the top of the top plate. So that looks good. I'm clumsy at driving this software. And now I've got that side bracket, and I can pretty much just drag it into position. I've made everything easy by going in even millimeter increments. So I can see that lines up the way I want it. That looks good. And this weird shape should be 3D printable that way. My only concern is whether the printer can print these tall, thin walls. These are 2 millimeters thick. This back one has to be 1 millimeter, so pretty skinny. And this plate here is 2 millimeters thick also. It doesn't need to be very structural. The assembly gets held by this lip here sitting on top of the neon bulb holder, and then this plate here going up against the front window for stability, and this whole thing sitting on top of the circuit board. And with a little piece of Kapton tape or something over here and a little piece of Kapton tape over there, it should be enough to hold it in position. And I've exported the STL file to my working folder. It's getting pretty late at night, so in the morning I'm going to fire up Prusa Slicer, drag in the STL file, and slice it, and then it should be off to the printer. And there I've dragged the STL file into my Prusa Slicer, and it looks like what I expect it to be. And now it's been sliced, and that's the way it looks in Prusa Slicer after the slicing process. Alright, I've got my Prusa i3 Mark III here, and I'm going to go to print from SD card. And my IM-103 light shield is the first one on the list. Checking file, heating the bed. It'll start printing shortly. Alright, printing has commenced. Looks like it's concentrating on making the holes first. Anyway, I'm not going to film the whole printing. But you can clearly see it's making the outline of the roof of the light shield, and that skirt that's around it just defines the overall size it'll be after everything's done. And now it's making that little flange off to the side. Yeah, it's pretty narrow. Back to this later. Alright, there's the finished print. It looks like the printer did not have any problem making that 1mm wide, tall, thin wall. And the 2mm wide side wall and this flange, I'm sure were less of an issue, but I don't see any distortion or anything. It did a good job of printing that. There's a better view of it. Now I wonder if it came out right. Well, that fit in there pretty as you could possibly ask for. It's not really trying to align the Nixie tubes. It just has those so it can fit tightly over them and not have the tips jam into something. On the other hand, if they start going really astray, then the holes will restrict their movement. The holes are larger because they're fitting so close to the top of the tubes that the tips are flaring out already, and at the bottom of the hole thickness, the diameter is considerably greater. The flange goes right up against the front window just like I wanted it to, and that 1mm thickness is just right to sort of wedge in there between the back of the left-hand Nixie tube socket and the lead of this shunt resistor. It just fits in there perfectly with just a little bit of friction. And of course it sits down along the circuit board there like you would want it to. And just for good measure, I put a little bit of Scotch tape on there. Don't know if it'll really be needed or not, but it doesn't hurt. And it certainly didn't hurt the way the thing looks. Oops. My temporary top panel of the meter slid off there. You can still see the tops of the Nixie tubes via ambient light going through the window, bouncing off and coming back out. I don't really think that light shield is necessary, but again, it doesn't hurt to have it.